As a last example, we'll consider problem 343, where we have a frictionless pulley mounted to a frictionless slider at B, around which is wrapped a cable that supports a weight of 30 pounds. We're told also that the pulley at D is frictionless, and that member BE is a bar. And for alpha equals 20 degrees, we want to determine the force in the bar BE and the reaction between the slider and bar AC. Take a moment now to pause the video and resume playing when you're ready to see a solution. Our attention is naturally drawn to the frictionless slider B, where all of these elements come together, and we're going to isolate that as a basis for drawing our free body diagram. But before we do that, we'll say a couple of things about the forces carried by these elements. First, it's important that both the pulley at B and the pulley at D are frictionless, because then it means that this single cable segment that begins at W and wraps around B and goes up to D and around this pulley and back down to the center here at B is all one continuous cable with a single tension. So when we isolate the slider and pulley at B, we're going to be cutting through that cable segment at 3 different locations, and there will be a single tension that's carried at each one of those cuts. We also have this bar BE, which we can see is pin connected at both ends, and if we assume that there's no intermediate force between B and E, and there is not, then that bar also carries a load along its geometry, and it will turn out in this case to be in compression. So it's a two-force member, and we know the orientation of the force in member BE. So we'll now draw an isolating surface around this pulley, and actually the isolating surface is more complicated than this, because there's going to be an external surface that cuts through the cable 3 times and cuts through the bar BE, and then there's an internal surface that's essentially separating the collar from the rod on which it's mounted, AC. So here we have the slider pulley at B removed from bar AC, and we'll note that we're cutting through the cable at these 3 locations, here, here, and here. The cable segment is carrying the weight W, so that's going to be, we're going to have a weight W here, and one here, and here. And it's not explicitly stated in the problem statement, but these cable segments between B and D are both assumed to be parallel to each other, and so in both cases we'll have an angle of 30 degrees between W and the horizontal, and we'll use a traditional XY coordinate system in our treatment of the problem. Now we're also cutting through the bar BE, and it will turn out that that will be in compression, so I'll go ahead and represent it as such. And we have this angle of 20 degrees on this side. And now we're not quite done, because we also have to separate this slider from the bar AC on which it's mounted. Now we're told it's a frictionless slider, so there's nothing impeding its motion along the slider AC. That means there's no reaction force in X, there's just a reaction force in Y, in this case a normal force that represents the inability of that slider to be pulled through the rod AC, and so I'll represent that as a normal force here. So N represents the force that's offered by the bar AC that's preventing this pulley slider combination at B from moving through it. So that will be our free body diagram, and we essentially have 2 unknowns. We don't know N, the normal reaction force, and we don't know the compression carried by bar BE. So we'll go ahead and write our X and Y force equilibrium equations. And in X we've got 2W cosine 30 minus CBE cosine 20 equals 0. And in the vertical direction, we have the normal force, we have minus W, and then in the upper right of our free body diagram, we've got two W's that are each making an angle of 30 degrees with the horizontal, so we'll have plus 2W sine 30 degrees, and then we have plus the compression in BE sine 20 equals 0. Now in this case, in our second equation, sine of 30 is a half, so 2 sine 30 is just 1, and the minus W term cancels out the 2W sine 30 term, and that gives me a particularly simple equation for n. So I've got the compression in BE is equal to 2W cosine 30 over cosine 20, and for W equals 30 pounds, that turns out to be 55.3 pounds. And then the normal force is minus the compression in BE sine of 20, and for CBE as 55.3 pounds, this is minus 18.9 pounds. Now you'll notice in this case that I got a positive value for the compression in BE, which says that that is in fact in compression, and the value of my normal force actually turns out to have the opposite sign to what I assumed, and that's fine. All that means is that the force that's exerted on this slider pulley assembly by rod AC is actually going down and not up. I don't have to change anything, I just make a note of the fact that the actual value of the force turns out to be in the opposite direction of what I've shown in the free body diagram.